Okie doke. Here we be. It is another one. Now we're going to move into what is called the integral test. Now the integral test, there's a couple rules for it. So we want to suppose f is a continuous, positive, decreasing function. All three of these must be true. Continuous, positive, and decreasing. And our x needs to be greater than or equal to 1. So if we have some sort of sum that starts at 1, goes up to infinity, and we can talk about the integral, and we can change those n's or those k's into x's. Now, if either both of them are going to converge or both of them will diverge. In the case of convergence, the value of the integral is not equal to the value of the series. And I wrote that wrong in the last one. I was writing that the limit is n tends towards infinity. Well, it will end up with the limits being true, but it doesn't necessarily turn out to be the same thing. I should have wrote a squiggly in there because we're dealing with sums. Okay, now I'm going to save you the proof. There's a lot in there, and I've been giving you a lot of the proofs and a lot of the whys. On this one, we're going to make sure that 3 things are taken care of. Let us attack a problem so we can see it. So we want to look at the sum as k is equal to 1 up to infinity of k over k squared plus 1. Now, all we're doing here is we're looking. Does it converge? Does it diverge? So we need to make sure if we want to do this, we want to be like, well, wait a second. This is like the same thing as 1 up to infinity of change all of your k's to x's. If we want to do this and we want to check it by doing the integral test, well, is it positive always? Well, yeah, your x values are positive. How the hell is this going to turn negative? So it's positive. Check. Is that continuous? Is that continuous? Sorry, I jumped it. Is there anywhere where you're going to get a 0 in the denominator? No. It's also continuous. Now, you don't have to write all this stuff down, but you better be right. Use the integral test when it's not positive. When it's not continuous, you're going to find out you didn't state anything. And lastly, but not leastly, we're wondering, is this a decreasing function? And I hope that you can tell that the degree up top is 1. And the degree down below is 2. And if that's the case, let me give you an example of one of those. It's called 1 over x. It's always, the limit is going to tend towards 0 as our x goes to infinity. It's going to happen. It's decreasing. So we have that. We're decreasing as well. And we already know that x is going to be greater than or equal to 1 because we started it with that way. So now what we can do is we just go find the integral of this. And if it goes to a number, dope. We're good to go. Now there's other ways to find out if it's decreasing. I don't like the way to find out whether it's decreasing. They take a derivative. Boo. They look at the first few terms. Boo. I'd rather use logic. But you can do it either way you want. So let's tackle this integral. So we have to write it as, we remember this from chapter 8. The limit is b tends to infinity of 1 to b of x over x squared plus 1. I don't think they make u subs much simpler than this. Do you remember? There's something called u subs. So let's call it x squared plus 1. du is equal to 2x dx. Let's divide by 2. 1/2 du is equal to x dx. And let's get it. So this is equal to the limit as b tends to infinity. Huh? Of b? Wait a second. Well, screw it. Let's just go. I'll be back for that in a second. I just want to do one thing at a time. So we're going to change our x squared plus 1 into u. And then we're going to change our x dx into 1/2 du. Let's leave the 1/2 up there. Who cares? But what about the bounds? We got to change them bounds, huh? We're going to do a u sub. We better do it. Sorry, I'm looking at something that looks real weird. Change the bounds. So if our u was going to infinity, this is still infinity, right? That would still be infinity. B is infinity, essentially. That's still going to be that. But what about the 1? I'm going to pop that in. 1 squared plus 1. Isn't that 2? So we changed our bounds. Now we can evaluate. So this is going to be the 1/2, the natural log of u, the absolute value, of course, from 2 to b. And oh no, I forgot my limit. And it's the limit as b tends towards infinity. We've done all this. So we have the limit as b tends towards infinity of 1/2 of ln of b minus ln of 2. That's just a number. But as we plug this in, that goes to infinity. Doesn't it? ln of infinity, big quotes around that. There's no such thing as ln of infinity. Goes to infinity. Therefore, this goes to infinity. So what we can say is our sum, since the integral diverged, the sum will diverge by the integral test. That is right, IT. We're going to have a lot of them. We're going to have CLT, CT, AST, DT. What else? Ratio and RT. Yeah, that'll be a few. So there's our first game. Let's try another one, okay? Let's mess with another one. Oh, let's check it out. From k is equal to 3. Don't care. Don't care. That 3 makes no difference. We learned about that before. That doesn't really make any difference. Oops, don't write dx. All right. So we're going to take a sum from k equals 3 up to infinity of 1 over the square root of 2k minus 5. Cool. So we might have to do a little bit of a, might need to do a little bit of a u sub here. Let's get it. Let's get it. So we're going to say, well, this is kind of equal to, start at 3, up to infinity of 1 over, and then you just change everything to x's, and then we're going to do the integral. So this is the same thing as the limit as b tends to infinity of 3 up to b of 1 over the square root of 2x minus 5 dx. And now I'm going to start to hustle because you know how to take integrals, don't you? U is equal to 2x minus 5. Du is equal to 2 dx. So we have a 1/2 du is equal to dx. Let's go. So this is equal to the limit as b tends to infinity. So the b is not going to change. 2 times infinity minus 5. Yeah, get the frick up out of here. And we're going to have 3 plugged into here, right, to get our lower bound. So 2 times 3 is 6. That's 1. Hey, look at that. 1 over the square root of u du. Oh, and I forgot my 1/2. There it is. Wait a second. Did I just start doing this problem without checking anything? Did I make certain that this is a decreasing function? Is this always positive? Is it continuous? Did we check? No, I just started doing the integral. I didn't check any of that stuff. Wow. We have to check. Is it continuous on the interval from 3 up to infinity? Yeah. X can't be 5 over 2. Can't be 5 over 2. Shoot. It can't even be less than 5 over 2. But 2.5 does not live in this interval, so we're good to go. Is it decreasing? Is there an x in the denominator? Is the degree larger in the bottom than it is up top? Yes, it's decreasing from 3 to infinity. Are all our values constantly positive? I'm pretty sure 1 is a positive number, and I'm pretty gosh darn certain that square roots don't pop out negative values, so I'm pretty sure it's positive. Oh, so it does work. Now, do you know how simple it would have been to be tricked if I just made this a 2? What if it was from k equals 2 up to infinity? Would it still be positive all the time? Would it be continuous? Would it be decreasing? No. No, it wouldn't. You could get tricked like that. So we really want to check. This one didn't matter. So the limit is b tends towards infinity of 1/2 the integral from 1 to b of u to the negative 1/2 power du. So we are going to get the limit as b tends towards infinity of 1/2 times u to the 1/2 times 2. Oh, those just cancel. Evaluated from 1 to b. So we're going to get the limit as b tends towards infinity of the square root of b minus the square root of 1. If that's going to infinity, we have infinity minus 1. This goes to infinity. Therefore, this diverges. Last one, doing it very fast. What about this sum here? From k equals 0 up to infinity of 1 over x squared plus 1 dx. Well, it's continuous. It's decreasing. And I'm pretty sure it's always positive. All right, let's do it. So we can now look at this integral here, saying this the limit as b tends towards infinity from 0 on up to b. And I wrote it as an x in there. Golly, and I wrote dx. Sorry. I'm not remaking this video. We're already 12 minutes in. Let's go. I'm just thinking, like, let's make it simple. That's inverse tangent. So we get the limit as b tends towards infinity of inverse tangent of x evaluated from 0 up to b. So we have the limit as b tends towards infinity of inverse tangent of b minus inverse tangent of 0. Well, as that goes to infinity, we know we get pi over 2 minus 0, which is pi over 2. That's a number. Since the integral converges, our sum also converges because it's continuous, decreasing, and positive. And by replacing the k with x's, doing the integral, we get to a number. It converged. Therefore, the sum will converge as well. Maybe we'll do another problem or two in here, but these are more about just getting in, doing work. I think we'll talk about the p-series real quick, and that should about end this section for the most part. Yeah, I think that's pretty good.